All right, so here are solutions and notes for the work-energy theorem. First one, describe the work-energy theorem in words and equations. So, in words, the net work done on an object changes its kinetic energy. So our equation for this is work net is equal to delta K, which is work net is equal to 1/2 mv final squared minus 1/2 mv initial squared, or I guess delta K would be like K final minus K initial. What's important is that it's the change in kinetic energy, not just the kinetic energy of an object. So, what happens to an object when work is done on it? The energy of the object changes. That's what happens when work is done on an object. The energy changes. And so, well, we'll just leave that off. It depends on what kind of work and energy we're talking about. But our big idea is that work changes energy. Now, we have different kinds of energy. There's kinetic energy, potential energy, chemical potential energy, gravitational potential energy, spring potential energy, heat energy. In order to go from one form of energy to another, work has to happen. That's how we change energy. If there's no work done, energy stays as the same kind of energy it has. It doesn't change at all. Can work be negative? Yes. Specifically for us right now, negative net work reduces kinetic energy. Energy is the ability to do work. For an easy explanation, it's a really good explanation. You could ask 10 different physicists and get 10 different answers. So the unit for work is the joule. It's the same unit, the unit for energy is the joule. It's the same as the unit for work. Kinetic energy is motion energy. If something's moving, it has kinetic energy. Kinetic energy is 1/2 mv squared. Doesn't matter which way you're moving, just matters that you're moving. Can kinetic energy be negative? No. One, there's no such thing as negative movement. The other thing that's proof, mass cannot be negative, and then even if you had -3 meters per second as your velocity, you square it, that ends up being 9 meters squared per second squared. So it is not possible to have negative energy. It must be positive. So a truck has a mass of 1,200 kilograms, a velocity of 35 meters per second. We want to calculate the kinetic energy of the truck. Kinetic energy is 1/2 mv squared, so that's 1/2 times 1,200 kilograms, its mass because it's kilograms, times the velocity, 35 meters per second, whole thing squared. So the kinetic energy of that object is 735,000 joules. When you're calculating that, be sure you square the energy of your object. So it's going to speed up, and it's going to have double the velocity. So now our kinetic energy is 1/2 times 1,200 times 70 squared. So that kinetic energy comes out to be 2,940,000 joules. If we want to know the factor by which it got bigger, kinetic energy from A was 1/2 mv squared. Kinetic energy for B kinetic energy for B is 1/2 mass times twice the velocity, and then that whole last bit is squared. So the kinetic energy for B is 1/2 m times 4v squared, because we're going to square both things inside of those parentheses. And so that gives me 4 times 1/2 mv squared. I know that mv squared is equal to the initial kinetic energy, so I have 4 times as much kinetic energy when we double the speed. That's what happens when things are squared. Find the work needed to accelerate the truck from 35 meters per second to 70 meters per second. So work is the change in kinetic energy. So work is the final kinetic energy minus the initial kinetic energy. So my final kinetic energy was 2,940,000 joules minus the initial kinetic energy, 735,000 joules. So the work needed for that whole thing comes out to be 2,205,000 joules. It's just the difference in the final and the initial kinetic energy. How much more energy did we have to give this thing? That's the work that we had to do. All right, next part, we have a cat, and we need to accelerate the cat to 5.5 meters per second. So work is change in kinetic energy, so kinetic energy final minus kinetic energy initial. So it's 1/2 mv final squared minus 1/2 mv initial squared. So if we start off at rest, that work is just going to be equal to 1/2 mv final squared. So that comes out to be 1/2 times 12 kilograms times 5.5 meters per second, whole thing squared. That ends up being 181.5 joules of work needed to get the cat to be going 5.5 meters per second. If the work is done over 10 meters, what's the force needed? So we have a distance and a force. Well, I know that work is equal to force times distance. So my work, 181.5 joules, is equal to the force, which we don't know, times the distance of 10 meters. So we'll divide each side by 10 meters. So that force is 181.5 joules divided by 10 meters, or 18.15 newtons. That's the force required. So for these next few problems, what we're going to be doing is finding the work using kinetic energy, finding the work using work equals force times distance, and getting our unknown from there. So we want to know the work needed to stop the car. Well, work is equal to the change in kinetic energy, or 1/2 mv final minus 1/2 mv initial. Both of those velocities have to be squared, don't forget that. For stopping, my final kinetic energy is 0. So my work is equal to negative 1/2 mass, 800 kilograms, times the initial velocity, 38, whole thing squared. So the work required to stop it comes out to be negative 231,040 joules. And it's negative because we're stopping. So we're taking energy away, but we're pushing against the motion. Negative work is going to reduce the kinetic energy. We're reducing the kinetic energy. We have to have negative work here. The car stops in 7.5 seconds. How much power is needed? To get power is work over time. Well, we got our work, 231,040 joules divided by the time of 7.5 seconds. So that power, it's negative, comes out to be negative 30,805-ish watts. Then for the next one, what's the work required to accelerate it to 85? So here, work is change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. So we're just going to plug our numbers in. So 1/2 times 800 times 85, because it's our final velocity, squared, minus 1/2 times 800 times 55 squared. And so our work here comes out to be positive because we're speeding up 1,680,000 joules. How much power is required to do this in 8.5 seconds? Well, power is work over time, so we're going to take that number, 1,680,000 joules, and divide it by 8.5 seconds. That comes out to be 197,647 watts. Again, we're just going to take that work, divide it by time to get to power. A car traveling with a velocity v requires a distance d to stop. What distance would be necessary to stop the car if we doubled it? So, situation 1. The work required to stop it is the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. That ends up being 0. So my work is going to be negative 1/2 mv initial squared. But my work is my force times my distance equals negative 1/2 mv initial squared. And we're going to call this force 1. Sorry, same force, I apologize. We're going to call it distance 1. So in our next situation, 2, force times distance 2 is equal to negative 1/2 m times 2v quantity squared. So if we square both sides, that's negative 1/2 m times v squared times 4. So I've made this side of the equation bigger by 4. In order to get this side of the equation bigger, d2 is going to have to be 4 times bigger. I need 4 times as much distance to stop. Car has a mass m and a velocity v. If it were to turn around, how would its kinetic energy change? No change. No change at all. Initial kinetic energy is equal to 1/2 mv squared. Final kinetic energy is equal to 1/2 m times negative v squared, which is the same thing as 1/2 mv squared. When you square something, the negative sign goes away. It does not matter which direction you're going, you still have the same kinetic energy, as long as you have the same speed. Rocket sled has a mass of 100 kilograms and an engine that's capable of this much power. We don't lose any work. What's the velocity after 1 minute? So here's how we're going to do this. If we start from rest, the work that we do all turns into kinetic energy because it's 1/2 mv final squared minus 1/2 mv initial squared. We start off at rest. So all of my work turns into kinetic energy. Power, I know, is equal to work over time. So if we solve that for work by multiplying both sides by time, we see that work is power times time. So for our time of 1 minute, the work is going to be the power, 187.5 watts, times the time of 60 seconds. So that work comes out to be 11,250 joules worth of work. Well, we're going to set that equal to the kinetic energy, so 11,250 joules worth of work is equal to 1/2 times 100 kilograms times the final velocity squared. So we'll divide by 1/2 times 100 kilograms on both sides, which is really dividing by 50, and then we'll square root it. So V final squared ends up being 225. So if we square root both sides, V final ends up being 15 meters per second after a minute, which isn't a ton.